So in this video, we're going to look at some more mechanical vibrations, but this time we're going to look at undamped examples. So I have some examples here. In the last video, I said I was going to look at one that already gave you the U thing, but I decided to just start with a full-on example, full-on word problem. So here, let me get my solution ready. So in this this is number 3. So in this problem, it asks us to find, this one's pretty simple. This is pretty simple. We don't have to do too much work for this one. It just says we have a mass, so let's write down all of our knowns. Now before we begin, remember, undamped means that our gamma is 0. We're in free motion. This I was messing up before. R is our range, our amplitude. T is our time for equilibrium position. Delta is our phase. T is our period. W is our frequency. Time to return to equilibrium position. Okay, so we do need that for this one. A mass of 100 grams stretches a spring 5 centimeters. So our capital, that is the capital L. The mass stretches the spring 5 centimeters. If the mass is set in motion, now from its equilibrium position, so something's pulling it down, right? Yeah, downward velocity of 10. Now remember, in this, the spring is getting bigger. So that downward velocity is increasing the size of the spring, so we're going to have a positive velocity. That's how I like to think of it. Right? Down is positive, up is negative. Okay, it wants us to find... Okay, I see. So we're given U prime is 10 centimeters per second. Oh, it's set in motion from its equilibrium position. So it's not pulled down at all. It's just let go. It's just... Well, no, it's being pulled down. Well, it starts from our equilibrium position for this one, so U would be 0. So these are our two initial conditions. I should write it like this. At time 0, 10 centimeters per second, and the position is 0. So now, we need K. We need our spring constant. Because remember, our equation is as follows. For undamped situations, this. We need the spring constant. We have the mass, we need the spring constant. We know that KL is equal to mg, as I explained in the last video. That's just from that's if you draw a free body diagram of the mass. We have the weight pulling it down. We have the spring, the force of the spring pulling it up. Right, that just comes from our free body diagram. Where was I? Solving for... Okay, now we have some unit issues here. Our mass is in grams. Our length is in centimeters. Our gravity would be in meters per second. So we can keep the mass as in grams. Why not? Yeah, let's do it so we can keep this in centimeters. So let's just convert the... I think it would be easier just to convert the... convert gravity into centimeters per second. So if we're going to convert 9.8, I'll use 9.8. Gravity is 9.8 meters per second squared. I want to convert it to centimeters, so that would be 980 centimeters second squared. So this would be times 980 centimeters per second squared. If you plug that into your calculator, or if you're good at mental math, 100 times 980 divided by 5 is 19,600. And the units would be grams per second squared. At this point, we don't really need the units. Well, maybe we do. I guess we'll find out. But that's our K. That's our spring constant. We need this. Okay. See, now everything's in grams. So we have 100 grams plus grams per second squared times u is equal to 0. If you solve for u, remember, propose u equals e to the RT. Take the first, second derivative, plug them in. All right, now solve for r. 0 plus or minus the square root of 19,600 over 100 This actually ends up being a really nice number, by the way. I, right, because it's imaginary. 19,600. Remember, if you're ever confused, I went over this very detailed in my last video. So go watch that one first. 14. Now remember, our frequency would be this right here. So our frequency is equal to 14. So that's... But it doesn't ask for that though. But it's still something to write down, you know. And that would be what? Grams per second squared over grams. Seconds? I think that's in seconds. Should be in seconds. 14 seconds is our frequency. Is it in seconds? Is frequency in seconds? Because think, we have what? Grams per second over grams. Maybe it's grams per second. I don't know. We don't really need units. This is math, right? We're not in physics right now. It is what it is. It's 14. I never had to worry about units for these. But if you do, it's easy to figure out. It doesn't even ask for W. Where was I now? Now after this point, right, we go right to here. C1, remember we propose our general, this is our general solution. C1, e to the 0t, cosine 14t plus C2, sine 14t Now we can say, let's take u prime. So we have this, right? Now we can take our initial conditions, which we have u of 0 is equal to 0, which is equal to, if we plug 0 in for our t's up there, we're left with c1 cosine of 0, so that's c1. So c1 is equal to 0. If we look at this one now, which is equal to 10, yep, centimeters per second. Are we in centimeters? Did I use centimeters? Yes, see, I kept everything in centimeters. So we're good. We don't have to convert that. So that can stay like that. Which would be equal to 14C2, right? So then C2 would be equal to 5 over 7. So here's my C1 and my C2. I'm going to use these when because remember, C1 is equal to R. We use polar coordinates, cosine of delta. C2 is equal to r sine of delta. To solve for r, I'm going to go ahead and solve for everything because why not? I know it doesn't ask for it, but I'm going... Actually, we do need it. We do need r. No, we don't, because it only asks for the time, doesn't it? Determine the position u of the mass anytime t. Okay, well that's just... Okay, well that's easy enough. We're already there. We already have that answer. That's just plugging C1 and C2 back into here. So that's just... This is what it was asking for. This is the position... That is the position u of the mass at any time t. But now say it asks for the amplitude, right? Then we would go down to here, and we have 0 equals amplitude cosine of delta. 5/7 is equal to the amplitude sine delta. We square these together, right? I can skip down to this. If you watched my last video, I showed how to get to here. This is the whole thing squared, by the way. So that's 25/49. Square root of 25/49, which is... Oh, that's just 5/7, yeah. Is equal to r. So that is our amplitude. So this would be our amplitude. Now if it asks for our excuse me, phase, which is delta, remember we divide these two equations together. We want sine over cosine, so we'd have 5/7 over 0. Oh no. Oh boy. That's undefined. Well, I guess we wouldn't... Well, actually, no, we still would have... Because it may be undefined, but what makes tangent undefined? Ah, jeez. Yeah, we can't do that, can we? Well, maybe that's why they only asked for the u. That would be undefined. Well, that's unfortunate. They do only ask for this. This is the final answer. So we can just skip the phase for this one. Let's ignore the phase. And then it asked us for... When does the mass first return to its equilibrium position? Well, first of all, the period would be 2 pi over the frequency, which is... Frequency was 14, I think. Yep, 14. Which is pi over... Well, let me keep it like that. Because all t is, or t equilibrium, is just the period divided by 2, which would just be pi over 14. Right? And this is the other answer that it wanted. Didn't want that. Only wanted that and that. Okay. So that's all it wanted for this problem. Pretty simple. This is one of the easier ones. Let's go to the next one. This one's a little bit annoying with the units. I will say that. And this is the last one. Yep, this is the last one. We have a mass weighing 3 pounds. We have a weight of 3 pounds. Weight is oops. Remember, free body diagram, mg is our weight. W equals mg. Force of the spring is equal to KL. mg is equal to 3 pounds. If mg is equal to 3 pounds, KL is equal to 3 pounds. Mass weighing 3 pounds stretches a spring 3 inches. If the mass is pushed upwards, contracting the spring, so the spring is shrinking. If the spring is shrinking, our initial distance would be negative. Yeah, negative 1 inch. Then set in motion with a downward velocity, downwards is positive, sorry, u of 0, of 2 feet per second. Of course, they go between inches and feet. Why would they not? And if there is no damping, find the position of U of the mass at any time t. So it asks for the same thing. And it also wants us to determine the frequency, period, amplitude, and phase of the motion. So that would be our W, our T, our R, and our delta. So first things first, we need the mass and we need K. Mass is equal to 3 pounds over 32, what is it? Feet per second squared? Yeah. So then our mass would be 3 over 32 pounds second squared per feet, or that's otherwise known as a slug, right? That's also a slug. Pound second squared over feet is a slug. I hate imperial units so much. It's so stupid. I wish this was metric. Anyways, we have our mass. We need our spring constant. Our length is 3 inches. Now, we should probably convert that to feet. Or should I? Yeah, I'm going to convert that to feet. So 3 inches in feet would be that's 3/12 of a foot. So that would be 3/12. So 3/12 of a foot. And I'm going to convert this one as well. This would be 12 times 3 is 48. Divided by 3 is 12. 12 is equal to, K is equal to 12 pounds per feet. Let me just double check my work here. Yes. Okay, now we can write out our modeling equation. So we have, I'm going to forget about units for now. Because everything should be in order. So we have R is equal to, okay, let me write this first before I get confused. So then we're going to have negative, let me just write it out. Oh man, what's 12 times 32? 12 times 32 is 384 over 3 imaginary. Let me see what that would be. 384 over 3. 8 root 2. Okay. So then our frequency, this is something it asks for, is 8 root 2. So we have 1 out of 5 things completed. We have our frequency. Now, let's find our position at any time t. So all we're going to do is propose our general solution for complex. E to the 0 t is 1. Cosine 8 root t, 8 root 2 t, c2 sine 8 root 2 t. Solve for c1, c2, take the first derivative. Negative, right? Cosine 8 root 2. Now we're going to have, we had u of 0 was equal to negative 1, right? That's from our initial conditions. Is equal to, if we plug in 0 up here for t, this becomes 1, this becomes 0, so c1 u prime of 0, I think it was 10, no, 2 for this one, is equal to, that's in feet, right? Okay, good. 2 is equal to, this becomes 0, this becomes 1. Oh, I forgot my C2 there. C2 would then be equal to 2 over 8 root 2. If we rationalize that, that would become 2 root 2 over 8. Is that what I have here? I just have root 2 over 8. What? What? I think I see a mistake here. Hold on. Give me 1 minute. Let me see if this is correct. Actually, that was okay. I just let's do it like this first, and then we can rationalize it, right? So then we have root 2 over 8 is C2. Okay. It asks us for the position at any time t, so we're going to plug in. So negative cosine 8 root 2 of t plus root 2 over 8 sine 8 root 2 times t. So that would be our position at any time t. So we can even write this as u of t. Let me just make sure that's what I have. My C1 is wrong. What? So where's my C1? Negative 1. What, am I missing something? Oh! I'm sorry. I converted it into feet, right? So it should be negative 1/12 of a foot. Don't forget about your units. Small change. Okay, so now that we have this, we can now solve for everything else. So we have a frequency, we have our thing. We need our period, amplitude, and phase. So the period is easy. Period is just 2 pi over w, which is just... So the period would be pi over 4 root 2. Or it could be root 2 pi over 8. So now we have a period, we have our frequency, and we have a function. We have a position with respect to time. Now, right, we use polar coordinates now. So we would have C1 is equal to our amplitude cosine delta. We have root 2 over 8 is equal to amplitude sine delta. We need to solve for these. We would have, well, let's solve for our range first, which would be, I'm going to go right ahead and square them already, right? To kind of skip the step there. What would that be? Okay, I have to put that in the calculator. 2 over 64 minus 1 over 24. That's not right. That's not what I have over here. 8 squared is 64. 12, oh my, 12 squared is not 24. It's 144. Sorry. I don't know why I multiplied it by 2. Happens. That's what, 7? Okay. Still not right. Still not right. Why? I have something different than what I have on my paper. But I have the same thing. Oh, wait. Maybe because I have to take the square root of it. Hold on. No, it should be the same thing. Oh, I just have a sign error somewhere. Oh, yeah. When I'm sorry. I squared that whole thing. It becomes positive. Okay. So then this would be 11 over 288. So then our amplitude is square root 11 over 288. Now, we have one thing left, our phase, right? So now we're going to do the division thing, where we're going to have sine over cosine. That becomes tangent, right? So this would be negative, what's 12 over 8? I don't know why I can't do that in my head. I'm tired right now. 12 over 8. Yeah, 3 halves. Negative root 2 tangent delta. Is that correct? Yep. So then our phase is negative 3 root 2 over 2. Inverse tangent, negative 3 root 2 over 2. And I believe that is it. So we got our phase, our amplitude, our frequency, our period, and our position with respect to, as a function with respect to time. And that's all it asks for, right? Position of the mass anytime t, determine the frequency, period, amplitude, and phase. Yep. So that's it for this video. So in the next one, I'll look over some damping examples. It is pretty much the same thing, except we just have an extra term in our modeling equation. But other than that, I'm pretty sure, it's been a while since I did damping stuff. But I'm pretty sure, like, let me see it. I think just our R would be different. Meaning, I guess maybe our general solution or our U function would be different. Oh yes, it depends on the situation. That's right. So you'll see what I mean in the next video when we get to dampening. So I hope you enjoyed the video, and I'll see you for damping.